The goal for today is for you to leave here feeling comfortable, confident in your ability to implement this resource in your classroom if you so choose, but also to, um, like I was just mentioning, also to open your eyes potentially to some different instructional strategies, different approaches to connecting students with data. And so feel free to pop questions in the chat along the way. You can see that this is a small group, um, and we won't have a guest scientist speaker today. So I suspect that this will last 40-ish minutes, and then we'll have plenty of time for questions, should you have them. So, so yeah, without further ado, I do want to mention, and for folks that just kind of arrived, if you weren't here last week, I talked us through a new data puzzle called Not All Warming is Equal, and it looked at differences in global atmospheric carbon dioxide concentrations at the surface over the last 100 years. And so there were areas over the eastern United States, China, and Europe where we saw significant changes in atmospheric carbon dioxide. And then a similar figure, but looking at changes in global temperature over the last 100 years. And we saw the Arctic, the northern latitudes getting really, really red. So rapid warming in the Arctic, but the people, the 4 million people in the Arctic, the few people in the Arctic aren't really contributing huge amounts of CO2. So they're experiencing this problem, right? Rapid warming, but aren't contributing to it. So some of the not contributing to in the ways that folks at lower latitudes are. So highlighting some of the climate inequities, who's responsible versus who's feeling the effects. And this data puzzle is really getting into challenging students to think about the mechanism by which the Arctic is, the mechanism driving Arctic amplification, the rapid warming in the Arctic. And so we'll kind of spill the beans here, and that has to do with this Arctic feedback loop that we'll talk about today with regards to declining sea ice, changes in albedo, and how that feedback leads to amplified warming in the Arctic. So different resources could be used in conjunction with one another is just kind of what I'm getting at here. So briefly introduced myself. I'm a former middle school science teacher with a background in climate sciences. So fortunate to secure this job with Ceres and get to work with some of my idols to develop resources to connect classrooms to contemporary science. So again, a talking head for a hugely collaborative team. My supervisor, Anna Gold, and my colleague, Elise, really have pushed this product and helped me develop these resources. Amy, our graphic designer, makes these lessons have a polish and pop to them that I think is really important. And then this resource wouldn't be what it is without Melissa Bratton, who's a co-author of Ambitious Science Teaching. So we'll talk about this here briefly, but data puzzles combine curated data sets from the scientists that we work with these ambitious science teaching practices that our collaborator, Melissa Bratton, has brought to the world and to this lesson. And so thankful for her contributions. And the featured scientist in this data puzzle, Dr. Jen Kay, really involved in outreach and has helped develop a number of resources, data puzzles, larger instructional units. So thanks to these folks and all the teachers that we've worked with that have piloted these, provided feedback. Again, this is really a hugely collaborative effort. Quick background. Our story starts back in 2019, years ago, with this historic Arctic research expedition. This is what I was hired to do, to tell the story and science of this expedition. And there were some really compelling Arctic data sets that we were including in weekly newsletters and in larger instructional units. And we developed a following. And when the field portion of the expedition ended, teachers wanted to continue to engage with Arctic science with contemporary data sets. And so I was looking for a way to take the data sets that were kind of buried in larger units and create a more concise product by which we could get these out more readily. And so worked with our friends and colleagues at Data Nuggets, an organization out of Michigan State, to produce a data nugget. So they do great work in the data analysis space for students. But we were seeking something that had a little bit more freedom. In my background in utilizing ambitious science teaching practices, I want to include some of those research-backed practices into this product. And so out of this, Data Puzzles was born, bringing together curated classroom data sets with these research-backed instructional practices to create a concise 2, 3, maybe 4 day product for students, supporting them and making sense of phenomena. If you haven't heard of ambitious science teaching, it's a pedagogical framework consisting of these 4 practices with many sub-practices or scaffolds embedded within these 4 parts, and tools for supporting meaningful, equitable science education. And so the practices as called out here, planning and engaging with important science ideas. You can think of these as the disciplinary core ideas as defined by the next generation science standards. How do we elicit student ideas and experiences as resources that we can call upon to support student sense making? How do we work with these ideas to support ongoing changes, and how do we press students to construct evidence-based explanations? And so ambitious science teaching, the book as written, is designed to support students or teachers, I'm sorry, in creating their own lessons or scaffolds to support their teaching in different ways. And so what we tried to do is use these practices to do the planning for you, to create lessons that include these scaffolds, tools, practices, so teachers don't have to create them. Hopefully they can utilize them as written in these polished data puzzle lessons in their classrooms. And so with Melissa's permission and the other folks from Ambitious Science Teaching, we've taken ambitious science teaching, those practices, and kind of shifted them around a little bit. So no longer in data puzzles are teachers planning for important science ideas, but they're identifying them. And so the 4 practices in data puzzles in each lesson start in the top right corner here, this eliciting students' ideas. We try to reveal resources, ideas, language, experiences that students have that they bring to the classroom in the context of an opening scenario. So this is an opening scenario that has similarities to the science investigation they'll engage with in the data puzzle. But before, for example, dropping students off in the Arctic and say, explore this concept in the context of the Arctic, a concept, a space maybe they've never thought about, maybe we can explore a similar concept in the context of their everyday life, that being the opening scenario, where we can bring out their ideas, experiences, and language about something they're familiar with, and then help them apply that familiar setting to a new space, a new concept that's included in the science investigation of the data puzzle. Next, through an interactive reading, we connect student resources elicited through this opening scenario to the science investigation presented in a data puzzle, and challenge students to develop some initial models and predictions about an investigative question. And students will test their predictions against an authentic data set in this 3rd quadrant here, and then they're tasked with putting all the pieces of the puzzle together, so to speak, to construct a final evidence-based explanation, which for most data puzzles is an annotated sketch representing an explanatory model. So this is the framework by which all data puzzles are written. This is what they follow. And so what we'll do now is explore, engage with this framework in the context of one of maybe 10 published data puzzles we have, this to reflect or not to reflect lesson. Before we dive into the 4 parts of a data puzzle in the context of this lesson, I wanted to take us quickly to this resource collection page. So this is the data puzzles homepage that you can access through the landing page. And so there are different data puzzles. Again, we're exploring different contemporary science phenomena, drought, a new data puzzle about shifting patterns of post-fire succession, ecological tipping points. The to reflect or not to reflect is one of the earlier data puzzle products. And when you click view resource, it opens to this homepage. All the home pages look the same. There's some background information, upcoming events, today's event here, and then the teaching materials, which include a teacher guide, slide deck, student worksheet. This is all meant to be plug and play should you choose to go that route, but they're also all available in Google Docs or Google Slides. So you can make copies of them for yourself and modify them as you see fit to meet the needs of your students. So again, what I did there was I clicked on this all lesson resources. So it's a Google Drive folder that includes everything linked on the previous page, but for you to see answer keys, the actual data set here, should you choose to have students plot points, a slide deck, student worksheet, teacher guide. I'll open a teacher guide just so you're kind of familiar with that. All of these teacher guides, again, are the same for each data puzzle. Some background and the different parts of the data puzzle. In this particular teacher guide broken out into 2 days. A second page has an instructional overview table that makes connections to the next generation science standards, has a driving question, some materials. This is where I've kind of hidden the answer key in the materials. So again, each of these data puzzles has an answer key and would encourage you to check that out before you get going. And then the 4 parts of the data puzzle described succinctly to try to keep the teacher guide to what I hope is a manageable 4 or 5 pages. I know when I was in the classroom, I did not like these 20-page teacher guides. I found them quite overwhelming. So this is what it looks like at the end of each teacher guide. There are some additional teacher resources. As you'll find today when we're engaging with the lesson, you will make connections like, oh, we could have brought this in here. I could connect it to this. And it's kind of by design. You can't put everything in these lessons. And so would encourage you to take them, use them as a starting point, bring them into an existing unit, or connect them to your curricula however you'd like. But again, different data visualizations, videos, articles that could be brought into the lesson should you choose. So that's what these teacher guides look like. If you haven't seen a student worksheet, they always look the same. There's a couple page text to start a puzzle plot that's often read as a whole class. There may be some visualizations or videos embedded in the text. And there's always an investigative question, a question that the featured scientist is seeking to answer. The second page challenges students to make an annotated sketch about some science idea that's presented in the text. So this functions as their de facto initial model. And then students record that investigative question and make a prediction about that investigative question. They test their prediction against an authentic data set and then are tasked with constructing a final model for the investigative question. So again, this is what each of the data puzzle lessons look like. The student worksheets all look the same, just with different text, different data sets, different model building activities. Great. So let's dive into this one. The first part of each data puzzle is this eliciting students' ideas practice. And the goal of this practice is to bring out student ideas about an opening scenario that has similarities to the science investigation presented in the data puzzle. And so These student experiences, ideas, and language, they can be really useful resources to help students make sense of new complex science phenomena. Different teachers have facilitated this part in different ways, but I think it's really important to note that these are not included in the student worksheet. So part one exists in the slide deck and is meant to be facilitated as a warm-up prompt, think, pair, share. We've had teachers facilitate this part in whiteboarding activities, or I even have seen student work of they have these markers that maybe you all have already seen this, but markers that you can write on a desk with and then wipe them down after. So meant to be something done individually or in small groups before a larger group discussion happens. But again, these are not included in the student worksheet, just the slide deck and meant to be facilitated by you collaboratively with your students. The opening scenario for this data puzzle is a video called Surface Matters, produced by one of our former colleagues here, Lynn Harden. She used to work for this California Academy of Sciences. And so in this video, an ice cream truck approaches this group of people who are laying out in the sun on a warm day. And this gentleman here has to make the decision about whether he wants to run to the ice cream truck, which is on dark pavement, in his bare feet, or whether he wants to put his shoes on. The last time he went and did this, his feet burned. But if he puts his shoes on, he might be last in line, he thinks, and not get the ice cream he wants. And so the idea is that students notice and wonder some different things about the scenario. Maybe it elicits an experience or memory from other students about a time they ran and barefoot on a hot summer day on some pavement and what that felt like. After watching this video, asking students to share what they notice, what they wonder, ask them to think about why the grass was cool and the pavement, the asphalt, was hot. Would be interesting to hear what students say. We can imagine what kind of language they would use. Maybe they're sharing other experiences. Maybe this elicits a totally different experience for them, or they remember why maybe they wear a white shirt rather than a black shirt on a hot day. So again, kind of getting at the concept of albedo without reflectivity of a surface versus like which are more reflective, which are more likely to absorb energy through a scenario they might be more familiar with. Bringing this to, we kind of introduce the concept of albedo after that scenario. The color of a surface matters. We start to talk about how some surfaces are more reflective than others, and it's got some communities, some cities starting to paint their roofs white and asking students to consider why some cities might be painting their rooftops white. Again, an opportunity to slowly introduce the concept of albedo through some different scenarios before introducing the featured scientist, Dr. Jen Kay, who actually studies the amount of sunlight, amount of energy that's reflected off the Earth's surface, the albedo of Earth's surface. And so Jen is an atmospheric scientist at CU Boulder, and she uses satellites to collect these albedo data sets. She's particularly interested in how sunlight reflects off the Arctic and how that might be changing in response to melting sea ice. So hopefully you can see with this opening scenario, we're going from some experiences, some scenarios the students may be familiar with or be able to connect with, and introducing the concept in that familiar way before saying, all right, and there are scientists that study something similar in a different place. And let's go learn a little bit more about Jen and her work and the albedo of the Arctic. So after doing this work, again, whether that's as a warm-up prompt, to think, pair, share, facilitating some whole class discussions, this is when I would distribute this actual student worksheet and say, all right, we're going to learn a little bit more about Jen's work as we enter into part two. This is the identifying important science ideas part. So Part two, the goal is to support students in identifying important science ideas that are introduced in an interactive reading called the puzzle plot. So again, we looked at the puzzle plot briefly. That 2-page text has graphics that serve as important discussion starters. They've got data visualizations, videos sometimes. So some different opportunities to pause and have some discussions with students as you're reading. It's important during this part two to work with students to connect science ideas from the puzzle plot back to the opening scenario. Give students an opportunity to summarize some of the key ideas through an annotated sketch that will serve as their kind of initial model. And then students identify and make a prediction about an investigative question. We've seen teachers facilitate this part in a couple different ways. I think most of the time we've seen classrooms read the text aloud together, and this allows the teacher to facilitate some class discussions as you progress. Other teachers have had students read them in small groups or individually. We would encourage you, if you use some close reading strategies in your classroom, to keep that consistency throughout and have students use those strategies as they work through that couple-page interactive reading. And the slide that you see here is directly from the to reflect or not to reflect lesson. And so kind of serves as this segue. We've just done the opening scenario. Let's learn a little bit more about Jen's work through this puzzle plot text, asking students to circle the investigative question and underline similarities between the reading and the opening scenario. This number 2 here, that will come back in each of the data puzzles after the puzzle plot text. There's a slide with a prompt designed to get students to support students in connecting the puzzle plot with the opening scenario. So a new space with a familiar space. Here's what we looked at this earlier, but here's what the puzzle plot looks like. Again, some background information about the satellites that have been keeping track of Arctic sea ice extent since 1978. We can see this decline in sea ice over that. What is that? 40+ year period. There's a link to watch a visualization that shows sea ice growing and shrinking each year with the seasons and overall shrinking over time. It kind of defines and describes albedo and shows a picture here of albedo of different surfaces, dark versus light. And then a couple paragraphs at the end introducing Jen and her work, the investigative questions she's trying to answer, among some other things. So after we've gone through that, here's what I was talking about, the question designed to stop and get you to think about how the opening scenario might connect to some of the concepts that were described in the reading. And then have students move towards summarizing these science ideas with a partner or on their own, where they draw and describe how sunlight shining on sea ice might differ from sunlight shining on ocean water and make a prediction about the investigative question. So this is the answer key. All data puzzles have an answer key. You can see this image here on the left is for students to annotate. You can see energy from the sun being reflected off of sea ice and absorbed by the ocean here. A little bit of text describing what's happening here, and then recording the investigative question: how might the Arctic's albedo be affected by the observed decline in sea ice? And students are going to be making a prediction about that based off of what they've read and what they've experienced themselves. After they've made their prediction, this is where we, the teacher, the facilitators, all right, let's test your prediction by looking at some data that Jen has curated for us. So again, these data have been collected by satellites, and then Dr. Jen K has kind of mined these data and curated them so they're in a usable form for this audience. And so that's how we transition into part 3. Let's test our predictions by looking at some data and some different facilitation strategies for this. We really would encourage you to talk about the graphs first with students before setting them free individually or in pairs to analyze the data, searching for patterns and trying to explain the patterns in the context of the investigative question. We've had a lot of teachers use this whiz-wim strategy, what I see, what it means, which basically challenges students to record observations directly onto the graph and then describe what those observations mean directly on the graph. So annotating a graph directly. And you may have some other strategies that you like to use in your classroom. So I'd encourage you to do that as well. In this data puzzle, we kind of force you, force students to think about where the data are coming from. And we start with a couple of videos. Again, everything in here is optional. It's that goes without saying. But what I meant to say is these are all Google Slides, so you can skip things, move them around if you so choose. But before we test those predictions, let's look at how these data sets were collected. So there are a couple short videos that talk about some of the instruments aboard NASA satellites that can measure Earth's reflectivity. There's a video here by NASA that talks about how these different instruments on satellites measure Earth's cryosphere, the amount of ice on the Earth's surface. And then I'll try once more here. I wasn't able to get this to load, but I think that this is a really cool interactive that allows you to click and view some of the different satellites that are circling Earth at any given time. And some of the instruments that Jen uses, the instruments that are collecting the data that students are going to be analyzing, these instruments are on the Terra Aqua, Sumi, and ICE satellites. And so it wasn't loading for me just before this event. And it looks like that's the case now, but would encourage you to check that out. In fact, I'll add this directly to the landing page. But I think this is a really cool opportunity to kind of allow for students to see not only the scientists, but see the satellites and the instruments that the data they'll analyze, like the instruments that were collecting them. So good context before the students analyze the data sets themselves. So let's analyze some of those data sets. Let's look at the amount of energy coming in and going out, that measure of albedo. Some slides directly from the slide deck. Over here, we have albedo on the y-axis. So reflectivity, higher values mean more reflective, more of the energy coming in from the sun is being reflected back into the atmosphere. Lower numbers means less of that energy coming in is being reflected and therefore more of it's being absorbed. And then on the secondary y-axis here, this is average September sea ice extent. And so each September, that's when the Arctic sea ice reaches its minimum. So the least amount of sea ice it will have during that year makes sense after the summer melt season. September representing the end of the summer. That's when we'll see this lowest extent. This is a data set from 2000 to 2018. I've just got data up through 2022, so I'll be updating this lesson here in the next few weeks with a more up-to-date, some more up-to-date values. But you can see there's clearly a relationship between albedo in the dark black line and sea ice extent in the dashed line, such that when there's more sea ice, the reflectivity of the Arctic is greater. So the lighter color, the white of the sea ice, reflecting that energy back into space. And when there is less sea ice, the albedo, the reflectivity of the Arctic decreases. So more of that energy is absorbed by the exposed darker ocean than is reflected back into space. So to support students in getting them familiar, maybe we talk about what these two different lines represent, how many years are represented, why are there two y-axes? And then in the student worksheet, and this is something you could discuss here, challenging students to identify a particular point and describe what it means. That's a strategy that Dr. Melissa Bratton, who co-authored Ambitious Science Teaching and worked with us here, she recommends just selecting specific points, having students try to describe those points to support them in becoming familiar with the data before asking them to identify and explain patterns. And then once you've had that conversation with students, then students would go off on their own or in pairs or in small groups to analyze and interpret these data in the context of this question. How might the Arctic's albedo be affected by the decline in sea ice? And then you, the facilitator, should be prepared with back pocket questions, as they're referred to, questions that can meet the students where they're at, questions that might be more designed to get them more familiar with the data set, or questions designed to challenge students to think about the patterns in the context of the Arctic and what it might mean up there. The final piece, after students have had a chance to analyze the data set, there's always a question too that asks them to reflect on their initial predictions. Did the data confirm or support their predictions? And then it's time to put the pieces of the puzzle together and construct an evidence-based explanation. And so this is where students are bringing in ideas from the opening scenario, evidence from the puzzle plot text, evidence from the graphs to construct an explanatory model. And so if your students haven't constructed an explanatory model, an annotated sketch before, there are slides in each of the slide decks for data puzzle lessons that will support them. And so in this context, we've gathered evidence through an interactive reading and some different data sets. So it's time to construct this final model for the question, how might the Arctic's albedo be affected by sea ice, the decline in sea ice? But what's a model look like, and what should be included? So many models, annotated sketches, often use signs and symbols so that there's not a ton of text. We can use arrows to show movement of things or connection between parts, zoom in windows, allow people to see what's happening on a smaller scale, keys, text boxes, timelines. So lots of different symbols. We've had teachers print this particular slide out and put it on student tables or desks so they have it to refer to as they're constructing their own model. So might be something to consider. And then having students think about these symbols in the context of a model that they might be more familiar with. So these models, they include relevant parts, connections, data, and evidence. So asking students to identify these different components, including the signs and symbols in the context of a Marvel movie, that worked for me in the classroom. And given that Marvel movies continue to be pumped out, I think my hunch is that many middle school, high school students are familiar with these movies, the Black Panther being one of them. And so the question that this model is working to answer is, why does the Black Panther get punched or get stronger after being punched? So it has to do with this element vibranium. You can see a key in a zoom in window that was deposited by a meteor, and how it's mined and then used in different suits and in the city in different ways. So trying to get students to see what we are expecting of them in a context, again, that they're more familiar with before asking them to do something similar in the context of the data puzzle. And so this is an example of student work, and I've actually included it in the answer key of an evidence-based explanation. In this context, the student selected two different time periods from the data set, 2001 and 2012. These squiggly lines represent incoming energy from the sun, and you can see when there's more ice, the squiggly lines coming in, many of them are going back out into space. Energy coming in is being reflected and going back out. The student used some numbers from the graph. So in 2001, they record the sea ice extent in September and the albedo for the Arctic during that time. You can see in 2012, there was less ice, 3.5 kilometers squared. That's not right, 3.5. There's another unit, kilometers squared. And the albedo for the Arctic, 0.48, I believe. And so you can see energy coming in, it's being reflected back into the atmosphere when it interacts with the sea ice, and then kind of being absorbed by the ocean, represented here in that model. So again, exploring and communicating the evidence from the interactive reading and the graph in the form of an explanatory model, making these concepts visible. After students construct this final model, there are opportunities to have students share their models with one another before the final piece here, which is this digging deeper question. So challenging students to put what they've learned into a different context or think about it in a different way. This is a visualization that's included in the slide deck in the lesson. And you can see the Arctic is getting warmer and warmer as students watch this visualization. And so we're asking students to think about how the decline in sea ice might affect temperatures in the Arctic. And so again, you have less sea ice, more of the energy coming into the Arctic is being absorbed by the darker ocean rather than being reflected by the light color of the sea ice. And so that is in fact what is driving the Arctic amplification. So global warming has led to a decline in sea ice in the Arctic. And as that sea ice declines, more energy that was previously reflected is being absorbed by the now exposed darker ocean, which leads to further melt of the sea ice, which leads to more energy being absorbed. And so that positive feedback loop, again, not a positive thing that's happening up there, but this positive feedback loop nonetheless, one thing reinforcing another, which contributes to that cycle. So this is a way to get at a mechanism driving Arctic amplification. And then Jen has produced about a 5-minute video that describes this positive feedback loop, the ice albedo feedback loop. So a way to bring it all home, and again, bringing Jen back into the picture here. So hopefully a really compelling story with compelling data sets to get students thinking about the rapid warming in the Arctic and why that's taking place. You can see that this might take a while should you, in terms of your class time, 180 minutes or more, I would say, if you open it up to having students explore the NASA satellites and you watch all of these videos with your students. So just something to consider. That's it for that particular lesson, and I'd love to talk more with you all about that with some questions here in a moment. Many of you have already seen this, but I'll just put a plug into the few upcoming webinars. These are actually the 3 newest data puzzles that we've produced. This wildfire, drought, and the future of forests, again, is a data puzzle that is designed to look at shifting patterns of post-fire succession. We're seeing what were previously forested areas in the Western United States transition to grasslands and shrublands after fire because of drought conditions. Snow in the Rockies looks at changing snow conditions in a Rocky Mountain watershed, and challenges students to think about how these changes might impact downstream users. And then winds of change, students are exploring wind patterns in Eastern Rocky Mountains, the Front Range, under changing climate conditions. So the 3 data puzzles coming up, different webinars, they all follow this same instructional framework that many of you have seen the last couple of weeks. So hopefully, if you can kind of understand what's available to you and how to facilitate one, the others will be familiar and maybe take a little less pickup time. That's it for me. I would love to entertain any questions now. I'm going to stop sharing. I have a question in the chat about putting a plug in this for other teachers associations. I would love it, Renee, if you put a plug in for these resources. I am excited to meet with school groups or groups of teachers. I don't necessarily have all of those connections, so I just throw this out onto some national listservs and try to develop relationships and connections that way, but would love to get into different school districts, groups, and work more closely with folks. So yeah,
So
appreciate it.
I'm actually the treasurer for the New York Earth Science Teachers Association. I noticed we have several people here from New York State. So thank you for allowing me to speak briefly about it. It's a relatively new organization. We've been around about 10 years now. You can find us at nyesta.org. I'll put it in the chat. Our membership fee is a whopping $20 a year. And we actually have a pretty good website. We had gone down a while bit, so we're still in the process of rebuilding it. But our main thing that we do that's been very helpful for a lot of people is we have an awesome conference every summer, and we travel around New York State and see different things. So this summer we will be at SUNY Potsdam, which is way north of almost on the Canadian border. So I'll put that in the chat, and if you would love to join us, or some of you may actually be members already, feel free to contact me, and I'll put that
Great.
in the chat.
Thanks, Renee.
Thank you.
Oh, geez. I also, if you thank you for being here, and here is a Google form. If you would like to get a 1-hour PD certificate from me, if you could fill that form out with your name and email, option to leave feedback, good or bad, would appreciate constructive criticism as well. Please fill that out and I'll get a certificate sent out to you via email, probably tomorrow. Anybody else got questions, comments, concerns?
I just want to say thank you for an excellent presentation again. I've unfortunately already finished all of my climate stuff for this year, but I look forward to putting all of this stuff in for next year.
Great. Thanks, Renee. Yeah, keep in
And I'll
touch.
see you on some more of these.
Would love to see that. See you a little bit more. Great. Thanks. Right on. Well, thanks all. Please reach out as questions come up. I'll ping everybody with the recording and the landing page and some other resources. But if anything comes up, if you have questions about this resource or other resources, or you want to talk more specifics, whether that's the science or the instructional approach, I would love to do that. My favorite part of this job is not sitting in an office by myself writing these. It's actually working with people and seeing people, whether that's in person or on Zoom. But yeah, please use me as a resource. And have a great Wednesday. Hopefully you're either finished with school or it's wrapping up here pretty soon. Thanks, Mike. Thanks for being here. Yeah, thanks, Ashton. See y'all. Bye, Renee.